Good morning. Myself Vijay Krishna, Assistant Professor, Department of Mechanical Engineering, SRM IST, Katangulathur campus. Today I am going to give the video lecture on the topic Introduction to Boiling from Heat Transfer Domain. So in boiling and condensation, convection plays a major role because it involves fluid motion. In boiling and condensation, combined heat transfer and buoyancy plays a major role here. Because of these two effects, there will be a large amount of heat transfer takes place. So this large amount of heat transfer takes place with small temperature difference. Though we are having large amount of heat transfer in boiling and condensation, it leads to a higher heat transfer coefficient also. There are significant parameters in boiling and condensation. So those parameters are latent heat, surface tension and buoyancy. Where we can find this boiling and condensation in application, so we can find it in a condenser of a steam power plant, condenser of a refrigerator, and we can see it in a boiler of a steam power plant. So apart from that, we can find it in a heat exchange equipment like heat exchanger, which will be used in the several plants like petrochemical, chemical, metallurgical plant also. And this two-phase phenomena, boiling and condensation, we can find it in the modern heat pipes also. When boiling occurs, so for boiling we need a surface and the liquid. So this surface should have a higher temperature when compared to a liquid. So the surface temperature should be greater than the saturation temperature of the liquid. So when the liquid comes in contact with the surface, the liquid phase will change from liquid to vapor. So when condensation occurs, so condensation is the vice versa of boiling, so in which the vapor state will be changed to a liquid state. So here if you see, here also we need a surface and we need a liquid, but the surface temperature will be less than the fluid temperature. How does the flow of heat transfer occurs in the boiling and condensation? So in boiling, the heat transfer takes place from surface to the fluid, whereas in condensation, the heat transfer takes place from the fluid to the surface. So the energy, here there is a phase change also, so we need a energy. So that energy, if you see, corresponding to the pressure of 1 atmosphere and saturation temperature of 100 degrees Celsius, the latent heat of vaporization is going to be 2257 kilojoule per kg. This is a saturation dome which will be used in the two-phase phenomena like boiling. This graph we can see that in y-axis we have a temperature and x-axis we have a specific volume and we have a curve. So this left side curve is known as a saturated liquid line, whereas a right side curve is known as a saturated vapor line. So these two curves meet at a common point. That point is known as a critical point. Let us take example here. So this point where it will be in a subcooled liquid condition, when we add the heat, the temperature increases, so it reaches to a point here. So this point is going to be a saturated liquid. So in this phenomena only the phase change will occurs. Let us take the case of boiling, the phase will change from a liquid. So this is the phenomena. Okay, here there will be a two-phase liquid plus vapor. Further adding the heat, it reaches a corresponding pressure and temperature, and this point is going to be a saturated vapor. In saturated vapor, if we further add the heat, it reaches a superheated region. So the other phenomena will happen in the vice versa for the condensation process. Dimensionless number. So in heat transfer subjects we have lot of dimensionless number. So in boiling and condensation there are two dimensionless number. One is Jacob number, another one is Bond number. Jacob number is the ratio between the maximum sensible energy and latent energy, whereas Bond number is the ratio between the buoyancy force and surface tension force. if you see in the phenomena of boiling, it is going to be an intensive vaporization. So the vaporization can able to begin at saturation temperature or slightly superheated, and also the boiling is possible in all temperature range. So here we can see that it can possible from triple point to the critical point. The values are also given for water that varies from 0.01 degrees Celsius to 374.14 degrees Celsius. Excess temperature. So this parameter plays a major role in boiling. Apart from previous parameter, there are other significant parameters plays a major role in quantifying the heat transfer in the boiling. One is temperature of the metal surface, that is can be called as a TW. TW is nothing but a wall temperature or surface temperature, and second is saturation temperature, that is corresponding to a liquid pressure and heat transfer at the surface. So in the case of boiling, the heat is transferred from the surface to the liquid. So we need to quantify the heat. That heat can be quantified using this relation Q equal to HA delta T E. So H is going to be a boiling heat transfer coefficient and A is the surface area, and this excess temperature is the temperature difference between the wall temperature and saturation temperature. Types of boiling. So there are 4 types of boiling. One is pool boiling, flow boiling, third is subcooled boiling, and last is saturated boiling. Pool boiling. So in pool boiling, it's similar to a natural convection phenomena. In the pool boiling, if you see, the water will be in the quiescent state, that is it will be in the very calm state, and will be constantly will be supplying the heat. In the figure we can see that bottom will be having a heating element and will be having a vessel. So from the heating element, the heat will be transferred to the liquid. The liquid will be in the very quiescent state, and the best example we can say like a kettle which is placed on the top of a stove or heater. And next is flow boiling. So flow boiling is associated with the forced convection. Here the heating element takes place through tube or channel. The heating element, either it is going to be a tube or channel. So inside the tube or channel we will be passing the fluid with some velocity. So that can be done with the help of external source like pump. Then we have a subcooled boiling. Subcooled boiling, how we can say subcooled boiling? We have a wall temperature and we have a saturation temperature. Let us take the wall temperature is 180 degrees Celsius. The saturation temperature is going to be 100 degrees Celsius. We have a water. If the water temperature is less than the saturation temperature, in the figure it is given like 90 degrees Celsius. When we have such temperature 90 degrees Celsius less than the saturation temperature, in that case what happened? Due to heating element, the bubble formed. But because of the subcooled condition, what happened? This bubble collapses. So such type of boiling is known as a subcooled boiling. Next is saturated boiling. Saturated boiling, we have a wall temperature, let us take 180 degrees Celsius, and saturation temperature is going to be 100 degrees Celsius. Now we are passing the heat, the liquid gets heated up and the bubbles will be formed, whereas in the subcooled the bubbles are formed and it got collapsed. But here it will not happen like that. The bubble tends to rise up because of the buoyancy force and escape from the free surface. So now we are going to see more detail about the pool boiling. So let us see what are the regions available in the pool boiling. So this curve represents different segments in the pool boiling. So we have a curve between the heat flux and excess temperature. Here we have a different stages. That different stages is categorized based upon the excess temperature. As I told earlier, excess temperature is nothing but the ratio between the wall temperature and the temperature difference between the wall temperature and saturation temperature. Okay. So if the excess temperature between 1 and 5 degrees Celsius, then we call it as a free convection boiling. If the excess temperature is between 5 and 30 degrees Celsius, then it is going to be a nucleate boiling. If the excess temperature is between 30 and 120 degrees Celsius, then it is going to be a unstable film boiling, or we can call it as a transition boiling. And last condition, between 120 and 1000 degrees Celsius, so such type of boiling is known as a stable film boiling. Free convection boiling. So, free convection boiling, if the excess temperature less than 5 degrees Celsius, we call it as a free convection boiling. So, in free convection boiling, we will be supplying the heat, and here we can see that we have a wall temperature 104 degrees Celsius, saturation temperature is also 100 degrees Celsius. Here the fluid circulated to the heating element because of the natural convection, and the liquid is slightly superheated here, and also in this free convection boiling, just we are transferring the heat, the liquid gets heated up. So, no phase change will occur, and this graph we can see that this is a between 1 and 5 is going to be a free convection boiling. Here we can see that as excess temperature is increased, the heat flux is also increased in this region. Next is nucleate boiling. So, nucleate boiling, if the excess temperature between 5 degrees Celsius and 30 degrees Celsius, then we call it as a nucleate boiling. Here in the nucleate boiling, the same thing, but next level. So, what happened? The vapor bubble begins to form here in the nucleate boiling, and in the graph also we can see that between 5 and 30, the heat flux, when we see the heat flux, gradually the heat flux increases and reaches the maximum point. So, that point is a D point, that is said to be a critical heat flux. So, when we design any equipment related to boiling, this critical heat flux plays a major role here. In the nucleate boiling also, we have two types of boiling. One is local boiling or subcooled boiling. Another one is bulk boiling. Subcooled boiling already we explained. Here the bubbles will be formed, but it collapses. It won't rise up and escape from the free surface. Whereas in bulk boiling, the bubbles will be formed, it breaks down, it reaches to the free surface because of the buoyancy force and escape from the free surface. Next is transition boiling. So, transition boiling, here the excess temperature is between 30 degrees Celsius and 120 degrees Celsius. So, here in the graph we can see that excess boiling is between 30 and 120. And when we check corresponding heat flux, what happened? The heat flux is decreased. Okay, the heat flux is decreased in the transition boiling. The reason why the heat flux is decreased here, actually what happened, the bubble formation is very vigorous here. Now nearer to the surface, once the bubble formed, it breaks down, it becomes a vapor blanket will be created here. So, vapor blanket will be created here. Now, because of this, we know that the thermal conductivity of vapor is less when compared to a thermal conductivity of liquid. So, there will be a hindrance in the heat transfer. That is why the heat flux is decreased here, and we are getting a minimum heat flux. So, that point is going to be a Leidenfrost point. So, maximum heat flux occurs in the point D, that is said to be a critical heat flux. The minimum heat flux occurs in the point E, that point is known as a Leidenfrost point. Then we have a stable film boiling. So, stable film boiling, the excess temperature is greater than the 120 degrees Celsius. So, between 120 and 1000 degrees Celsius is said to be a stable film boiling. So, here we can see that the heat flux is increased. How the heat flux is increased? Because already there is a vapor blanket. Now, what happened further? Through conduction and radiation, the heat is transferred from the vapor to the liquid surface. That is why the heat flux is increased in the stable film boiling. Now what happens if you further the heat transfer takes place between the vapor and the liquid, the heat flux is going to increase and it goes to a point D. Sorry, it goes to a point F. Okay, it goes to a point F. When the boiling condition reaches the point F, what happens? It is unsafe for the material. Because it reaches the maximum, it reaches the melting point of the material or above than that. So when we keep on adding the heat, what happens? It cracks the material, it leads to a unsituation condition. So it is not advisable to operate any device with related to boiling after the point D. So that is the point we want to get it from this graph. So finally, I want to share the what are the references I referred for this material. Thank you.